and thank you for this nice conference and having me here. So the main question I'm going to address in this talk is superconductivity a quantum or a classical phenomenon? So we learn from textbooks and all sorts of other sources that superconductivity is a macroscopic quantum phenomenon. But on the other hand, the theory of superconductivity is a mean field theory. And mean field approximation combined with Ehrenfest's theorem imply that the theory is classical. And I will show this explicitly for the theory of superconductivity. So this suggests that superconductivity is in fact a purely classical phenomenon in contradiction to textbooks. So let's take a look at the celebrated Bardeen-Cooper-Schrieffer theory of superconductivity. Consider fermions moving in some arbitrary single particle potential with energy levels epsilon k. So for example, this can be atomic fermions in a harmonic trap. So the first term in the Hamiltonian captures that, and then the second term is a pairing term which hopes Cooper pairs from one level to the other. So for example, this term here takes a pair from level k and puts it on level j. Singly occupied levels, on the other hand, are annihilated by the interaction, and therefore they are decoupled. So then, on each level, we either have nothing, it's unoccupied, or it's doubly occupied, which means that we can describe it with a spin 1/2 variable. So then we say that the spin is up if a level is occupied, and it's down if the level is empty. So these spin variables are called Anderson pseudospins. And then spin lowering and spin raising operators are pair annihilation and pair creation operators. In terms of Anderson pseudospins, the BCS Hamiltonian takes a form of a spin Hamiltonian with infinite range ferromagnetic interaction in the xy plane and in homogeneous Zeeman magnetic field along the z-axis. So now let's write down Heisenberg equations of motion for this Hamiltonian. So for spin, these are always Bloch equations, and we see that each spin couples to the transverse component of the total spin L. Now, the BCS mean field approximation replaces this quantum variable, the total spin L, with its quantum mechanical average, which I will call capital L. And then we have a spin moving in its own magnetic field. And because each spin is moving in an individual magnetic field, the wave function of the system is a product state of individual spin wave functions. So this is the famous BCS wave function written in terms of spins. Let's take the quantum mechanical average of these equations of motion. And we see immediately that what we have here is that the averages of spins, these capital SJs, they behave as classical angular momenta of fixed length. And that these equations of motion are actually Hamilton's equations of motion for this classical spin Hamiltonian. So you could say, so we reduced equations of motion for a superconductor to a classical Hamiltonian. But you could say that there are, maybe some quantum fluctuations beyond just taking these averages. But it turns out that, in fact, BCS mean field is exact for the ground state and low-lying excited states in thermodynamic limit. So the physical argument goes as follows. So first of all, we know that mean field is typically exact for models with infinite range interactions. Specifically, in this particular case, since the total spin is sum of a large number of spin 1/2s, we expect its quantum fluctuations to be negligible compared to its average, as long as the average is macroscopically large. So for the low energy state, since interaction is ferromagnetic, the average is of order n. and fluctuations indeed should be small. But on the other hand, for highly excited states, this average is of order 1, and mean field is not necessarily exact. Moreover, there is actually a rigorous proof due to Richardson that mean field is exact for low energy states. So the thing is that the BCS model is beta ansatz integrable, and using this beta ansatz solution, Richardson was able to show that mean field is indeed exact for the ground state and low-lying excited states. Furthermore, all observable equilibrium properties of superconductors, such as excitation spectrum, Josephson effect, topological properties for topological superconductors, can be obtained from this classical spin Hamiltonian I showed a couple of slides ago. So we therefore conclude that equilibrium superconductivity is a purely classical phenomenon. Now, in the past 15 years, there have been a lot of work on far from equilibrium superconductivity. So this work is motivated by experiments in ultra-cold fermions and also by terahertz palm probe experiments on superconducting films. And all relevant results in these papers, and there is a paper about one paper a week roughly these days. So all results are obtained within mean field approximation. But far from equilibrium, the system is in a superposition of all states, and far from equilibrium means that the energy is thermodynamically large. It scales as n. So then highly excited states contribute to the dynamics. And we know that for these states, mean field is generally invalid. So, in all these 15 years, people have been asking this question, but are we allowed to use mean field far from equilibrium? I mean, is it still valid, or maybe it breaks down? So far from equilibrium means that we are interested in a unitary evolution with the BCS Hamiltonian. So a natural way to initiate such evolution, for example, in ultra-cold atomic fermions, is to drive the system by making the superconducting coupling vary in time. So then what we need to solve is a time-dependent BCS Hamiltonian. So what do we need to do to determine if mean field is exact? So first, we need to solve the non-stationary Schrödinger equation for the quantum time-dependent BCS Hamiltonian in thermodynamic limit exactly. Then we also need to solve classical equations of motion for the classical version of the BCS Hamiltonian in the same limit to obtain this capital Sk, and then from that we can reconstruct the mean field wave function. And then finally, we need to compare the exact quantum and exact mean field wave functions. So this sounds like a nice program, but unfortunately, solving for the time evolution of a macroscopically large number of interacting quantum particles or spins with a time-dependent Hamiltonian is basically impossible, both numerically and analytically, even when your underlying model is integrable, such as, for example, one-dimensional Hubbard model or the XXZ model or Linear model. But it turns out that the BCS Hamiltonian is special. So its integrals of motion are not just any integrals, but they are so-called Godin magnets. So here is the K Godin magnet. It describes spin Sk subject to a Zeeman field to B and interacting with all other spins. So here B is equal to 1 over twice the superconducting coupling constant. So if we trade G for B, we have to write the BCS Hamiltonian like this with a coupling constant 1 over 2B. So the statement here is that these guys all commute between themselves, and they also commute with the BCS Hamiltonian, which is in fact their linear combination. So the reason Godin magnets are special is that they describe endpoint correlation functions. So these are functions of all these epsilons and b in SU2 West-Zumino-Witten conformal field theory. So the correlation function psi satisfies n compatible equations of motion of evolution type, which are known as Knizhnik-Zamolodchikov equations. So nu here is an arbitrary parameter, and epsilons are the same epsilons that occur in the Godin magnets and that play the role of single particle energies in the BCS Hamiltonian. So in addition to epsilons, we have one more parameter in this correlation function. And it turns out that its evolution with respect to this parameter is governed by nothing but the BCS Hamiltonian. So here, in this evolution equation, I have the BCS Hamiltonian on the right-hand side. Okay, so what do we have? We have this evolution equation, and this is the BCS Hamiltonian with coupling 1 over 2b. So let us substitute b is equal to nu times t in this equation. Then this equation 1 becomes a non-stationary Schrödinger equation for the BCS Hamiltonian with the superconducting interaction strengths inversely proportional to time. 1 over 2 nu t. So fortunately, this is exactly the kind of time dependence that you would get in ultra-cold fermions if you change your detuning from the Feshbach resonance in time. So by changing the magnetic field, the external magnetic field, linearly in time, your coupling constant in the BCS Hamiltonian is going to change in this way. So a natural problem in this context is to start in the ground state at t equals 0. This corresponds to infinite superconducting interaction in the BCS Hamiltonian, evolve to distant future and determine the asymptotic wave function. So the state at 0, it minimizes the interaction, and because the interaction is ferromagnetic, it corresponds to having the maximum total spin equal to n over 2 and a certain z component of the total spin, which corresponds to a prescribed number of electrons that is fixed initially. This state also, by the way, is a maximally entangled state of n spin 1/2. So now what we're interested in here is a many-body version of a Landau-Wiener problem. So we have the system initially in the ground state, and we evolve it. It now can make transition because the interaction depends on time. It can make transition to excited states, and we want to understand with what probabilities is going to occupy the ground state and various excited states. So we are going to use this many-body Landau-Wiener problem to test the accuracy of the mean field approximation far from equilibrium. So here is how we are able to solve this problem. The thing is that there is a general formal solution of Knizhnik-Zamolodchikov equations. It is incredibly complicated, much more so than, for example, a beta ansatz for the one-dimensional Hubbard model. So it is in terms of an n-fold counter-integral over off-shell beta ansatz states weighted by something that is called Yang-Yang action, and we weight by exponentiated Yang-Yang action. Nevertheless, this also, as we discussed, gives automatically a solution of the non-stationary Schrödinger equation for the BCS Hamiltonian with coupling inversely proportional to time. And even though this solution is incredibly complicated and at the first glance appears to be useless for any practical physical purpose, it turns out that at t going to plus infinity, it simplifies dramatically because the integral localizes to the stationary points of the Yang-Yang action. And all we have to do is to determine this stationary point, which means to solve beta ansatz equations in certain limit, and then sum over such stationary points and take thermodynamic limit. So we do this for spins of magnitude 1/2, and this gives us exact quantum solution. And then we also send the magnitude of spin to infinity, and this gives us the classical solution. Okay, so now I will describe the final answers. So here is the exact quantum solution. So the time dependence is in these exponent here, this lambda alpha and theta alpha are phases that depend on epsilons, are constant phases. And I should have said first that this is written here in the natural basis of occupation numbers, in that simple basis. So the state here, alpha, is so this alpha, the set alpha, is a set of doubly occupied levels. So for example, if this alpha is equal to 1, 2, 3, I know that levels 1, 2, 3 are doubly occupied and the remaining levels are empty. M is a total number of Cooper pairs. And because the state is an eigenstate of a total number of Cooper pairs, it's more convenient to write it like this. I will denote the state, psi of t plus infinity, as m infinity to also indicate the number of pairs that it has. And also, finally, what I first described, this term, and this term, these are just phases. And the weight of the state is given by this factor, e to minus pi alpha over nu. And notice that it's independent of epsilons. Whatever epsilons you take, the probability of having the state alpha is the same. That's a signature of time-dependent integrability. And also, I want to stress that this answer is exact for any number, for any n single particle levels arbitrarily chosen, and arbitrary number m of fermion pairs. Like you can take, for example, n equals 3, m equals 1. This is still going to work. Or you can take n equal to million and m equal to 500,000, and it will again work. So here is the exact classical solution. So, here I switch from the spin language back to the original fermion language. So this is a BCS type wave function. And here are this UK and VK known as Bogoliubov amplitudes explicitly and exactly. So the time dependence has the same form as in the exact quantum solution. This phi k is some phase that depends on epsilons. And again, the probability of this or that state is encoded in this zeta k, which is independent of epsilons, and which is simply given by this expression with mu be playing the role of chemical potential, and in the large n limit given by this equation. Okay, so now we can compare the classical and quantum solutions. And the third main result here is that mean field is exact for local observables in the thermodynamic limit. So basically, local observable is an observable that involves little n operators such that this little n divided by the total number of levels goes to 0 when the number of levels goes to infinity. Okay, so the most general such operator is this O, which is product of this little O's. Each of these little O's is either a pair creation or annihilation or level occupancy operator. So any other combinations of creation and annihilation operators on averaging will give you 0 expectation value. Okay, so the precise statement is that averages of local operators in the exact asymptotic state coincide with the expectation values in the mean field wave function in thermodynamic limit. So now it can be that this operator O changes the number of pairs. Like, for example, the pair creation operator increases it by 1. So to allow for that, I define the average in the exact asymptotic state as a matrix element between exact asymptotic state with m pairs and m plus l pairs. So for these pair creation operators, L will be 1. So this, so defined average is equal to expectation value, which is just regular expectation value in the mean field wave function. And it's simple to determine the expectation values in the mean field wave function. They are product of expectation values, and each of the individual expectation values we can write in terms of this Bogoliubov amplitudes, which we know explicitly. So not only we can assert that mean field is exact, but we also can compute the averages of any arbitrary local operator in the asymptotic state. And corrections to mean field, we find that they are of order this little n over n. So you already see that if this little n is going to be of order n, capital N, mean field is not going to work well. And indeed, we see that the classical description, mean field description, breaks down for global measures, both in equilibrium and out of equilibrium. And the simplest example of this is an entanglement. The thing is that the mean field wave function is a product state and it's unentangled. So its entanglement entropy is equal to 0. On the other hand, we find that in exact ground state, the entanglement scales as log n, log number of levels. And even if we start the exact quantum dynamics in an unentangled mean field ground state with 0 entanglement entropy, the entanglement grows monotonically according to this formula, and it saturates at S entanglement of order log n. Clearly, mean field with 0 entanglement cannot capture these results. A more interesting example is the Loschmidt echo. So Loschmidt echo, defined by this equation, it's the amplitude to return to whatever initial state I have after evolving it for time t. So this is essentially the partition function of the system in imaginary time. And we know that for regular partition function, its singularities as a function of temperature or other system parameters signal phase transitions. So by analogy, it is believed that singularities in the Loschmidt echo indicate certain dynamical phase transitions. Okay? So here is what we find. A purely classical mean field analysis shows numerous singularities in the echo for S-wave BCS superconductors and none for P-wave. On the other hand, quantum analysis shows diametrically opposing results. It shows no singularities for S-wave and periodic singularities for the topological P-wave superconductor for the evolution that starts from a quantum critical point at 0 chemical potential that separates the topological and non-topological phases. And the reason for the failure of the mean field is that it determines the bulk of the system wave function. Like it determines the system wave function with good accuracy, but only, let's say, 99.9% of it. But the echo is in the remaining part. It's amplitude of having this state, and that's exponentially small. So the Loschmidt echo is determined by exponentially small tails of the wave function. So now, let me also draw a conclusion from here, generally for all mean field models, because, there is, in this sense, nothing special about superconductivity. So we believe that mean field theories are able to capture the order parameter and other local observables, but the entanglement and other many particle structure of the quantum state are out of reach, both in and out of equilibrium. So in this sense, there is no difference between being in equilibrium, far from equilibrium, okay? The status of the mean field is not affected by that. So, and we know that mean field theories, enjoyed quite a bit of success, but this success secretly relied on the fact that order parameter is usually a classical object, like in our language here, is a local operator. If it were a non-local operator, then the thing wouldn't work. And last but not least, let me acknowledge my collaborators. So Jet Pixley is my colleague at Rutgers. Angun is, his student who did a lot of numerical work on this project. And Aidan was my student and also Jet's student, and he already graduated. Thank you very much.
Thank you. Let's thank Emil for a very nice talk. Questions? Yeah.
Thanks for a very interesting talk. So I might have missed something, but your initial state is, are you assuming some? Yeah, so is it, I got a little bit confused because the final state that you're, so first of all, what's your initial condition? Sorry.
The initial condition is the ground state of this Hamiltonian, with coupling equal to this, 1 over 2 nu t, at t equal 0 plus. It means that this thing is plus infinity. So basically, the ground state is the ground state of this term.
I see.
With a minus sign. So that's a state where the total spin has a maximum value. I mean, it's also a state that you get in superconductivity at infinite coupling, infinitely coupled superconductors. It's a state where the total spin is equal to maximum because I have n spin 1/2, the maximum is n over 2, and the z total is something given, like, is a variable. Like, that depends on how many particles you want to have.
So yeah, the thing that I wanted to ask is like at the t equals the infinite limit, is that a finite temperature state sort of, or is it like a ground state of some Hamiltonian?
So that's a very good question. Well, I mean, first of all, any state that you give me is a ground state of some Hamiltonian. Yeah, it's a pure state, so it's a ground state of some Hamiltonian. You just write psi psi. So this state is non-thermal. So basically, I mean, I didn't discuss this here and didn't write this here. So the probabilities of occupying the state alpha, the probability is related to this factor. It's a product over alpha of all factors like this, with alpha included in this state. So it's non-thermal state, but it's described by a generalized Gibbs ensemble. So it is a generalized Gibbs ensemble steady state. But it's not, strictly speaking, finite temperature state. It's a gapless superconductor state.
I see. Thank you very much.
Yeah.
Related to your last statement, is a generalized Gibbs ensemble because secretly the model is integrable, is better integrable?
So in this case, I mean, it's very interesting. It's not, the same as generalized Gibbs ensemble that you would see, for example, if you quench the Hubbard model or something like that, or any other model, because that model has integrals of motion.
Right.
So this is emergent generalized Gibbs ensemble. In a sense, I'll explain in what sense. So I don't have any integrals of motion. These go down magnets, they still commute, but because I made the coupling time dependent, they are no longer conserved, strictly speaking. But at infinity, this term goes away, and my integrals are simply this SKZ. So I have emergent integrals. It's an emergent integrable system, and these are exactly this SKZ are the integrals that will occur in GGE.
I see. Thanks.
More questions? Yeah. Okay.
So you said that the local variables are exact while the global ones are not exact in the comparing the quantum and classical one. But does the 2-point correlation function count as the global one or the local one?
Local.
Okay.
2 point. You have to have infinite points for it to be global.
I'm a little bit confused because you said that dynamical phase transition cannot be kept. I mean, the result of whether there's a dynamical phase transition or not will be captured in. I mean, will be there in classical but not in quantum. But I would have thought that can be captured by looking at the 2-point correlation function, and I would have thought that there will be a singularity in the classical one while not in the quantum.
Okay, so this Loschmidt echo, Loschmidt amplitude, it involves infinite number of like creation and annihilation operators, right? In this exponent. So when I said 2-point correlation of functions are local, I meant equal time.
Equal time.
But if times are unequal, it's not local.
I see. Interesting. Thank you very much.
Okay. Any more questions? So maybe I had just one question. Regarding this n-point correlation functions, let's say equal time, it can be n-point correlation function as long as small n by capital N goes to 0 as n goes to infinity, right? So in that sense, it can be non-local, but still as long as the fraction goes to 0 in the large n limit, right? So, like for
Yeah.
example, if
so-
small n is n power 0.8, then it should still be
So
valid.
I think you are saying that I can have like 1 and then n, which is far away.
Right,
Is that in that sense it's non-local?
right,
In my
right,
definition, is local.
right, right.
Okay, yeah. So you see, this, it does not have any geometry because it's all-to-all interaction. How I picture that, I mean, if you want to picture it on a chain, how you do it is up to you. Like if you select, let's say, 1 and n,
Right.
I will rearrange them and put them next to each other, and that will make it actually, I can take all these things for which I'm computing the, correlation function and put them next to each other.
Right.
And then in that sense, in that basis, sort of, in that like way of labeling, the length of that segment goes to 0 as n goes to infinity. So it contracts to a point.
Right.
So
Okay.
local is, in that sense, like very well defined.
Okay. Okay, thanks. Okay, so if there are no other questions, let's thank Emil again for a very nice talk.